give you an important example of a structure that's important in the context of this summer school. So this is part of the, let's say, the Harry Howard the important person now is Lemma. So I think that in Valerian's slides from last week, I saw a triangle denoting the Holy Trinity, which is natural reduction, desummation, like calculus, and completed those categories. So Curry and Howard observed the correspondence between natural reduction and the simply type lambda calculus, and Lambeck observed the correspondence of those with completed those categories. So let me explain some of that. So we're going to let T, so remember last time, or even the time before, we talked about the syntactic category for any type theory T. So now I'm going to somewhat fix a T. So let T denote a type theory with the structural rules of the simply like lambda calculus. We have like the variable rule, weakening, protection, like that. And I just want to consider a fragment of what people usually mean by the simply type lambda calculus, so it doesn't get too complicated. So let's say that we also have the rules for the unit type and the rules for the rules for the product type. Okay, so we have some simply type lambda calculus here, and I want to think about the syntactic category associated with this type theory, and that's the category of all the types and terms that I can build up. But a little bit of a problem because I haven't really specified enough here for that collection of terms and types that I can build up to be interesting. Okay? Because I have the unit type that exists. I have the unit times the unit. The unit times the unit times the unit. Those are all at least isomorphic to the unit. So it's not very interesting. In particular, it will be the terminal category, the category with just one object and then the morphism on that object. Okay, so I want to add some extra stuff. So I want to have constant symbols for types. So let's say I'm just going to fix a set C of constant symbols for types and constant symbols, let's say little c, for terms. So I have two sets of constant symbols for types and terms. And then with those constant symbols, I can generate a more interesting syntactic category. Okay? Because I'll have constant symbols coming from here, and I can take the product of them, and something like that. Okay, so this gives us, this whole thing is going to give us the syntactic category that we keep mentioning of our guy T. And now I want to say that there is a functor from C of T to D, where D is any category with terminal object and product. Given by the following. So we have here basically a programming language, I mean a category that represents a programming language, and we want to define a functor into a category. And I'm going to say that this functor is like the categorical realization of an interpretation of this language T into a category Z. Okay. So whenever we're defining an interpretation, maybe some of you have seen things like this before, we do it by structural induction on the language, right? So the language is built out of these things, and we're going to say that this is going to go by structural induction. So we need to give, we need to say where the generators go. So we want to say it's given by specifying, let's see what notation I use here. Let me give this a name. So it's given by specifying f of t, let's say, for all t in our set of constants c, and it's given by specifying f of c, let me say f of little t. So this is an object, f of t is an object, and f of little t is a morphism. Okay. For all terms that we have in our set C of constant terms. And we got condition right here. So we want to have a third condition that the unit is mapped to the terminal object. Let's say f of unit we want to send to the terminal object of all capital T. Oh, I use capital T over there. Maybe I use fold 1 for the terminal object. And let's say that f of two objects in this category, so let's call them S and T. We take the product of S and T. We want that to be mapped to the product where we send S and T. Okay. So if we think about these conditions, they look a little bit different, right? So with these, I want to say definitely we want to send the unit to the terminal object and a product to a product. With these two conditions, I don't really care where you want to send the constants, but you just have to choose them. So this is kind of the only choice is reasonable, and here you have three choices. For every constant symbol, for every type constant symbol, you have to choose an object, and for every term constant symbol, you have to choose a morphism. Okay, and this produces a functor. Okay? And that's because this whole thing, this whole category is generated by this kind of stuff. So once we say where it goes, it produces a functor. Maybe someone have a question? Yeah. We have a set of terms, the term symbols, and a set of type symbols. Okay, so maybe it's an exercise to really prove that this is a functor. Okay. I'm wondering what I should erase now. So let's do things a little bit more, with a little bit more information. Okay, so hopefully you guys remember what type theory you're working with. Basically, the simply type dynamic calculus as it's usually presented without function types. Everything that I'm saying is also true for function types. And then on the categorical side, it's usually called like exponential or exponentiated objects. But I won't define those because it would take too long. But it's also true. Okay. Yeah.
So simply type dynamic calculus, but we don't have function types. We have product types.
Yeah.
Do we have that in type?
No.
Okay.
That's usually not included in simply type dynamic calculus. But we definitely could if we wanted to. And then on the categorical side, we would, like here, we want to interpret these type formers in specific ways. If we had the empty type, we would want to interpret it as an initial object. Okay, so now I want to define a new guy. Let's call it kernel m of t. And this is going to be a category with the following. So for topics. But currently M is supposed to stand for models. So this is going to be a category of models of T, or a category of categories which have interpretations of T. Okay, so the objects are categories with terminal object, products, and interpretations. Let me give it some name. Interpretation. Use this symbol. Interpretation of little t for each type symbol t and term symbol little t. Okay, so these are the categories. These are the objects, they're categories. And the morphisms are going to be structure preserving morphisms of categories, which are functors. Okay, so you can do wacky things with categories, but usually when you have a category, the morphisms are the normal structure preserving morphisms, like the obvious thing that you can come up with that preserves structure. So we have categories with structure, so we're going to have functors, and morphisms of categories that preserve the structure. We want to preserve the terminal object and products and these things. So if I won't write everything out, but for example, we might have a functor f between two categories equipped with all the structure, and then we want to say that f of the terminal object in C is the same as is the same as the terminal object in D. Okay, questions? Yes.
Maybe you've said so and I've overheard. What are the morphisms in C of pi?
Yeah, so
What
this
is
is
F?
a capital T. This is a bold T.
Ah, sorry.
Long word bold
Sure.
T. So it stands for the type theory. And the morphisms are terms. So the objects
okay,
are
so the
types,
terms are the morphisms. Okay, then
and
that
the
makes sense.
morphisms are terms.
Okay.
Yeah, so to produce a functor out of it, we have to say where the base objects go and the base
Yeah.
morphisms go. Yes.
Maybe you just answered that. The little c is just the morphisms of the category.
Yeah, I read it now, sorry. But the little c was the set of term constants. And the terms in the syntactic category, the terms become the morphisms of this category. So the terms of the type theory become the morphisms of the syntactic category. Yes.
So two quick questions. In the original type theory, the terms are morphisms?
No, so we just have normal type theory.
Okay.
Normal, simply typed lambda calculus, like Julia was talking about. Your category theorems, you look at that, you go over our obvious arrows drawn, and I certainly think about them as morphisms. I've completely conflated type theory and category theory. But we just start with a normal old, simply typed lambda calculus with a normal kind of notation, like this.
So in the original one, are the morphisms like the deductions, or what are the morphisms in
So T is a type theory, so it doesn't have a notion of morphisms. It just has a notion of types and terms.
Okay. And the other question I had was, do morphisms generally have to preserve products, or do they not really guarantee that kind of result?
Yeah, functor between categories definitely doesn't have to preserve products. Yes.
And so again, think about the morphism could be your key category. And it's like all weight type terms with a whole or function type, like
So
or
we don't have function types in the type theory we're talking about right now. We definitely put everything I'm saying is true, but just that's more detail I can put on the board right now. So we don't have any function types. The morphisms are really just coming from terms. So if you write a term like this down in the type theory, then this is a morphism from A to B.
Term is one free
Sorry?
variable. Term is one free variable.
Yes, yes, yes.
The objects is with a single interpretation.
Yes,
So is that also saying the objects are the functors on the right half of the chalkboard?
so this functor is going to be a morphism in this category. So the objects are categories with this kind of structure. So in particular, hopefully it's obvious that D, by this choice, D has this kind of structure. So D is definitely an object of this category. And we'll also see that this is an object of this category, and this is a morphism in this category.
Okay, I guess I can just ignore it for now, but I wasn't quite sure how to interpret interpretations in the part of the object description. That felt like it had some functorial content referring to like the original syntax category.
I'm trying my best to make it look different than that, but it is exactly the same as that.
Okay.
Yeah. Yeah, so I mean here, we have to choose where to send a T to from the syntactic category, like one of these generating types in the syntactic category to some object in D. And here we might just, we're not talking explicitly about the syntactic category in the background, but we just have a category T. And we want to say where, a category D, and we want to say where a T goes.
Okay.
And I'm not mentioning the syntactic category explicitly.
Okay. I'll be quiet. Thanks.
Any other questions? Yeah.
So, in your example up there for the term, which is a morphism in our category C of big T, would B be a morphism in B, so from B to B, or would it be a morphism from A to B?
Yeah, so this kind of thing, how should I write it? So this,
Mm-hmm.
so this is in T,
Yes.
and then in C of T, we have a morphism like this.
Okay, good.
Okay, yeah, so we see something like this in T, and we get a morphism like this in C of T. Yeah. Yeah, so I'm sweeping a lot of details under the rug to fit this into this week. So definitely you can still model this when you think about context with multiple things. Maybe then I would say this category has objects context, but then having like multiple contexts, you do just like product them up and pretend that it's one type. Or you could represent this in a multi-category. Like there's a lot of choices, and I'm trying to do the simplest thing I can. Yeah. Yes. I mean, this is definitely a type of judgment for B. Yeah, so in this category, the morphisms are typing judgments. Yeah. Yeah. Okay. Okay, so here we have the syntactic category. Now I want to talk about a different category, the category of models or interpretations. So we have categories with basically interpretations of the structure of the simply type lambda calculus. Now I'm trying to keep them separate. Now I want to observe, I want you guys to observe that this category, the syntactic category, is a category in here. Right? Because we showed before explicitly that it has products yesterday, I think. It definitely has a terminal object, but it doesn't say explicitly, but hopefully you believe me that it corresponds to the unit type. And it has interpretations, it has choices of an object for every type symbol T, and a morphism for every term symbol little t, which is just the type in our type theory T that becomes an object in the syntactic category TT. So, CT is an object of M of T, and this kind of data becomes an object of empty. And so we've shown already, or I've explained, that there is one morphism, at least one morphism, from this guy, this object of empty, to an arbitrary object of empty. Okay, so this, I said this is an object, but this is really arbitrary. Right, choosing, getting a category with a kernel object and products and choosing these interpretations is exactly the same thing as having a category with kernel object and products and choosing these interpretations. It's the same thing. So I've argued that there's one morphism from this special object of empty to any object of empty. And now what do you think? Yeah.
That means that it's the initial object?
Yeah. So we would need to make some arguments that there is exactly one morphism from this guy to this guy. Maybe I'll leave the details that you can write down to you guys. But what's really happening is that what composes this is, I think, the structural rules of the type landing calculus, which really don't guarantee that this is a category. Then we have the rules for the unit type and the product type, and the constant symbols, capital C and little c. So if we want to describe an interpretation of the type theory into any other category, we just need to say what it does to all those generators. Okay. And that's what we're describing here with this data. Okay, so there is a morphism out of CT, and it's unique given this kind of data. So, in fact, in particular, CT is the initial model, is the initial object. You have to write that precisely. Is the initial object of empty. Right. So the intuition, as I said, is that its initial, and this is maybe a question line, its initial, because to define maps out of it, you have to, if you want to define map out of it, you can do it via pattern matching. Basically, you look at the constructors of this category, which are the same as the constructors of the type theory, and you say where they all go, and then you get a map out of it. Okay, so let me not prove or really explain the true lambda correspondence, but I'll just state it. Okay, so this is to lambda. I think 1980 wrote a few things about it. So he showed that category of, let's say, now, extensions of the, what I've given here. So simply times lambda calculus without function types. So I mean, now just like the structural rules, type and product type like we were talking about before. In what I was discussing before, adding the constant symbols was producing some kind of extension of that basic type theory. Okay, so we have extensions of the type theory with just the normal rules. But not function types, I just don't want to define them right now. So the category of extensions of the simply type linear calculus without function types is equivalent to the category of categories with in one direction. So I haven't, haven't defined this word. We don't have time, unfortunately. But we talked about isomorphism between two objects in a category. We could also talk about two categories, thinking about them living in the category of categories. You can think about two categories being isomorphic themselves, which would mean that we have some more stuff. Which would mean that we have two categories like this with maps back and forth, such that GF is the identity on C, and FG is the identity on D, and it looks like this. Okay. But then when I have an object, let's say of C, I can plug it in here to this functor and see how it acts. So that I would have for every object X of C, GF apply to X is the same as doing the identity to X, which of course is just X. Okay, but now I have an equality of objects, which I said before is kind of not what we do in category theory. So actually we want to ask that this is isomorphic. And so really I want to ask that these two functors are isomorphic. But I haven't really defined what it means for a functor to be isomorphic to another functor. But now I'm just giving you the intuition about what's happening here. Yes?
So equivalent sort of means isomorphic in the category of categories, or
Is weaker.
equivalent is weaker?
So
Because you just want, okay. If they were isomorphic, then you would get that.
Yes.
But if they are equivalent, then you get isomorphism.
exactly.
I see.
Yeah, so we definitely have a notion of isomorphism of categories, where these two symbols are literal equalities. And that's kind of weird because that involves talking about equality of objects, which we don't like. So if we replace equality of objects with isomorphism of objects, then we get a weaker notion that is equivalence. So we ask basically that these are inverses of each other, just up to isomorphism, not up to equality. So it's a weaker notion because isomorphism is a weaker notion of sameness and equality. Yes?
Sorry, just to clarify, when you said two categories are isomorphic, you meant two space categories, right? And not two dash categories.
Yes, and I don't think I have mentioned two
Okay,
categories
I just-
in the lectures.
Sorry, okay.
Trying not to do that, yeah. There's only two categories going around here, but I think I got that out loud so far. Okay. So, yes, I just wanted to explain very briefly what this word equivalent means, but it's the appropriate notion of sameness between two different categories. Isomorphism is, like I said, kind of suspect. So the category of extensions of the simply type lambda calculus with our type constructors that we have introduced is equivalent to the category of categories with terminal objects and products. And for equivalence, we need functors back and forth. But we have certainly described a functor in one direction. So we have described a functor, well, I only have one shot today. So we certainly described a functor in this direction from simply typed lambda calculi to these kinds of categories. And that was given by this thing. Okay, so we take a simply typed lambda calculus or an extension of the simply typed lambda calculus. So we extend it with some constant symbols, maybe also some equalities that I didn't mention very explicitly. And then we form the syntactic category and we get one of these. Okay. And then we can also think about the models, which are other categories in here, which there's a morphism out of this way. Yes?
What is the minus?
It's like a blank, it's a hole.
Oh,
Because we had a bullet T there before.
oh, okay.
Yeah.
Yes.
Yes.
I'm still slightly confused just about, so I understand that we can turn T into a category by putting C around it. That means T itself is not a category.
T is a type theory.
T is a type theory. Okay.
T is a type theory. It has a syntactic category CT. But probably not right now because you're still like compiling all the things that I told you. But in the future, when you get used to it, you can definitely end up with should conflate T and CT.
Okay.
Because they have the same information. Just think about how it's packaged differently. Yes?
So in practice, when someone says, oh, I'm giving a category of semantics for a language, is this what they're doing?
Exactly. So, unfortunately, I erased the definition of the category of models purely out of T. But giving an object in that category is giving a categorical interpretation
So like
of T.
specifically an object and then also a functor from C of T to that.
Yeah, so you can either think that you have, like, let's say, given T, you can either look at objects in empty, so those are the models of T. Or, so this is option one, option two, you can look at objects in this category here, the category of categories with terminal objects and products. So we call an object in there like control C. It's hard to read. In here, with a morphism from C of T to, what we call this C, we're going to call it D. To D. If. So you can look at an object D in this category of categories with terminal objects and products. You look at a category with terminal object and products, and you ask if there's a morphism here. And this is the interpretation. And maybe I can just hint at the fact that with 1 more hour, so it's not very hard to explain, I can explain just with categorical mumbo jumbo, abstract nonsense, how to define this category from this category. You know about post-set theories and stuff, what David talked about before, it's like the downside under CG. Okay. Right. So this is kind of the upshot, this important theorem of Landbeck, but quick first start questions. Yeah.
Just wondering if the categories of terminal objects parts has a lead, or is it just
Maybe Lex.
Lex?
Yeah. That's probably the name. Yeah. It stands for Lex of Lex. Yes. Any other questions? Sorry. Less exact. Any questions? Okay, and then I also want to say, of course, that I've just given the simplified version so that I could define at least most of the concepts in this theorem. But it's definitely true, I wish I had a different color, but it's definitely true that if I delete this and I say